So my task is to introduce the first speaker, who is Sir Simon Donaldson. A tradition is to sort of list the speaker's accomplishments, but I won't do that because there are far too many. I will say to people out there, any young people who don't know, Simon, in Greek mythology, Athena was not just the goddess of wisdom, but the goddess of mathematics. So Simon's mathematics is certainly blessed by the goddess herself. Simon.
Well, thank you for your invitation to this talk. It's a great honor and pleasure. And thanks to Cliff for his, I'm sure, completely undeserved introduction, which is much appreciated. So these two talks will only touch on perhaps a part of what might be indicated by the title, the connection between algebraic geometry and Kaehler Einstein metrics in particular, also more generally the connection between algebraic geometry and differential geometry. So let me begin with some sort of background before getting on to the particular questions and developments that I will want to discuss. So the problem we're considering will be to take a compact, symmetric complex manifold, and we want to ask about what kind of preferred metrical structures might there be on this. And we restrict attention to Kähler metrics, which is the class of Riemannian metrics which fit in best with complex geometry. And there are many ways of expressing this. One is to say that if we have any Riemannian manifold, that defines the notion of parallel transport, so we can transport tangent vectors from one point to another one. If we have a complex manifold, then of course we have a way of multiplying tangent vectors by I, and one formulation of the Kähler condition is that these two processes to commute. Multiplication by I commutes with parallel transport. But there are many other ways of saying that. So we want to look at Kähler metrics, but if we have one such metric, then there will be many. So what conditions could single one out? The conditions, which are very natural and belong with historical and other reasons for considering them, as we'll explain. One condition is to consider Einstein metrics. Of course, this is something we could do in general in Riemannian geometry. This is just when the Ricci curvature is a multiple of the metric tensor. So we can put these two together and consider metrics that are Kähler and Einstein. Another thing which turns out to be of interest is to look at the scalar curvature. So in general, remember, in Riemannian manifold, this is given by taking the trace of the Ricci tensor. And we can look at the condition that this scalar curvature is a constant. Of course, both of these, if we go down to complex dimension 1, just to Riemann surfaces, both of these become the same. They both essentially boil down to the Gauss curvature of a surface. We're looking for surfaces of constant curvature, and of course, we know a lot to say about that. The simplest example being to take the complex projective line, CP1, which of course is a sphere, the Riemann sphere. If we think of it as the unit sphere in R3, then we can see, of course, it has a metric of constant curvature. And on the other hand, we know that if we take surfaces of, say, a negative Euler characteristic, then they can all be covered by the unit disk, and that induces metrics of constant negative curvature. So these are different ways of extending those ideas to higher dimensions. And we also we'll restrict attention to the algebraic-geometric case. That's to say, we fix the Kähler class, as it's called. Should be a fixed integral class. It's not so important if you're not so familiar with this background, which means that fixing this data, the cohomology class of the Kähler class, is the same as fixing a line bundle over X. And the sections of this line bundle give an embedding of X in projective space. So the central question then is we want to have some way of deciding in terms of just the complex geometry, or more precisely in our situation, the complex algebraic geometry, in terms of some algebraic variety, when does it admit one of these special metrics, a Kaehler Einstein metric or a constant scalar curvature metric? That's the basic question we want to discuss. We seek an algebrogeometric criterion. So for today, as in the title of the talk, we will mainly restrict attention to this Kaehler Einstein problem. So let's abbreviate to KE. Well, there are the three cases depending upon the sign of this lambda. If lambda is 0, then one studying what are called Calabi-Yau manifolds. And this was the problem famously solved by Yau in the 1970s. But in fact, under this condition, if we have a manifold with it's required, the manifold has first Chern class 0, then we always have such a metric. Similarly, if lambda is plus or minus 1, then what that means is that this line bundle has to be the canonical bundle or its dual. So that L is equal to Kx, the opposite sign, where this is the usual thing. This is the maximal exterior power of the cotangent bundle. So this is a restriction on the kind of manifolds that one can consider, that we need either the canonical bundle or its dual to be what's called an ample line bundle, which corresponds to giving some embedding in projective space after taking a suitable power. But we can we consider the situation if lambda is say equal to minus 1, then again this is the case that was solved the same with era by Oban and Yau. we always have existence. Just generalizing in a simple way what we know about Riemann surfaces, that we always have these constant curvature metrics. So the harder case, as lambda is +1, this is the hard case, comparatively speaking, then we're saying that the dual of the canonical bundle is an ample line bundle over our manifold. This is just what algebraic geometers call a Fano manifold. And it's been known for a long time that this is a harder case because there are obstructions to having a straightforward existence theorem. There are obstructions to show that we can't just have a theorem saying such metrics exist in complete generality. The oldest, going back to Matsushima in the 1950s, if we have a Kaehler Einstein metric, this implies that the automorphism group of X, which will always be some complex Lie group, but it must be a reductive Lie group. So one can write down examples of Fano manifolds where this property is not satisfied. This is something determined entirely by the complex geometry. And then it follows that they don't have these Kaehler Einstein metrics. For example, we could just take the complex projective plane and blow up in one or two points would give such an example. So the question is, the answer has to be more complicated because of this, and many other obstructions were discovered subsequently. So this goes back to the 1950s. So this is what I want to tell you about is the solution of this problem. About the question of the existence of Kaehler Einstein metrics on Fano manifolds. And although I won't really have time to talk about it, it fits into a larger problem which is not solved, and not by a long way, of asking if we have a more general situation of when we have a metric of constant scalar curvature. When we go beyond the world of these Fano manifolds, or essentially manifolds of general type, where we have these, considering in this situation. So before we really embark on that, let's just spend a few minutes talking about the nature of the question. So this is, what I want to do is to write down what these problems are in terms of local formulations of the complex differential geometry. We'll make essentially no use of this later, but I think it's important to have this sort of, useful to see explicitly what the problems involved are, and also I want to explain what may not be obvious, the distinction between these two problems, the constant scalar curvature and Kaehler Einstein problem. So let's just review some complex differential geometry of how we can write this problem down as an explicit partial differential equation. So if we take some reference Kähler metric, say omega tilde, then the well-known piece of theory says that within this fixed Kähler class, any other metric is given in terms of a Kähler potential. So we can write omega in terms of a single function. We have this fixed thing plus I dd bar of phi, or more explicitly in local coordinates, ZA, this would say that the metric, the coefficients of the metric tensor are given by the reference one plus these mixed holomorphic and anti-holomorphic derivatives of our potential function. So this is the metric tensor. Another thing would be the volume form, V, in local coordinates, which is just given by the determinant of this metric tensor. Then there's a relatively simple formula for the Ricci curvature and the scalar curvature in the situation. Let's just say the scalar curvature will be given by taking the Laplacian, but with respect to the metric omega of the logarithm of V. So the equation we will be solving, the constant scalar curvature equation, will be this fourth order differential equation in which you first of all take this nonlinear expression, this kind of called Monge-Ampere type expression, and then you take the Laplacian and put another differential operator, but the coefficients of this operator depend also upon the metric. And you want to solve that that thing is equal to a constant. So this is a fourth order, very nonlinear PDE. So we could think about these Kaehler Einstein metrics as special cases of these constant scalar curvature ones, but it turns out that if you're in this situation when you have this special choice of the line bundle, then the Kaehler Einstein conditions can be expressed in a much simpler way as second order PDE. We can integrate out two of the apparent derivatives in the equation. So the KE equation well, in general, a more geometric way of thinking about this Kähler potential, as it's called, is as a Hermitian metric on the line bundle you're considering. The Kähler form appears as the curvature of the Hermitian metric. So in this situation, our line bundle is, say, kx to the minus 1. And then if you think for a moment, you see that giving a metric on this highest exterior power, or its dual, is precisely the same algebraically as giving a volume form. On X. So if we have a metric on this line bundle, then we have two ways of getting a volume form on X. One is by this corresponding metric situation, by taking, then we have the V, and we also have this algebra geometric construction, theta H. And the Kaehler Einstein condition reduces to the second order PDE that these things should be equal. So this is a second order equation of sort of Monge-Ampere type because it involves this taking the determinant of this complex Hessian matrix of second derivatives. So let me that's the end of the first introductory question, the section in which we've explained the problem we want to discuss. Secondly, I'm going to recall some background in the area what you might call stability in the sense of geometric invariant theory and differential geometry. So there's a circle of ideas here which one could approach and try to explain in various ways. One is by saying that the the way we'll take it is say that a prototype is a theorem of Narasimhan and Seshadri. From 1960s, which concerns holomorphic vector bundles over a complex curve or compact Riemann surface. So to explain the statement, let's recall the definition given by Mumford shortly before this time. Supposing we have a holomorphic vector bundle over a Riemann surface, a compact Riemann surface, let's, to simplify our discussion, assume that the first Chern class of E is 0. Then we say this is stable if for all proper subbundles, F in E, then we have the C1 of F should be less than 0. That's the definition. And the point is that Mumford wrote this definition down from considerations purely of algebraic geometry, the questions about forming moduli spaces of holomorphic bundles over curves. Whereas Narasimhan and Seshadri's theorem then is that E is stable if and only if it admits a, let's just say, irreducible flat unitary connection. Well, we don't even need to think really about connections here. We can just think of a flat structure, whether E can be given by a system of locally constant transition functions with values in the unitary group. But the crucial thing here is that we've got unitary connections. It's a much rather easy observation of Weil that any holomorphic bundle of Riemann surface admits a flat connection for a general linear group. So the crucial thing here is the unitary condition, which of course is not a something outside purely complex geometry. So there'll be many later developments in this direction that we don't have time to say anything systematically about, but we have to write down the names. Let's say it's a Theorem bot, Uhlenbeck, Yau, Hitchin, Simpson, and so on. Many other statements in the context of Yang-Mills theory, which is talking about connections and holomorphic bundles of a similar nature, relating algebrogeometric notions of stability to the differential geometry of unitary connections. But we can also give another completely elementary example. Well, so let's say, so these sort of fit into a general pattern, a general scheme, which has been understood quite well for 20 or 30 years now, which roughly speaking, we will have some family of complex geometry objects. And then we will have some preferred metrical structures which a priori might or might not exist. And then we will have a criterion for existence involving degenerations. This is a way I choose for today to summarize this rather extensive circle of ideas. So in this Narasimhan and Seshadri discussion, our complex geometry object would be a holomorphic vector bundle, something purely in complex geometry, algebraic geometry. Our preferred metrical structures would be these flat unitary connections. Our criterion is in terms of these subbundles appearing in the definition of stability. It's not obvious what that has to do with degenerations. That comes about because if you take a bundle E and a subbundle F, then you could consider another bundle, which is just taking F direct sum E over F, and E degenerates to F direct sum E over F. So it's quite simple to write down a family of holomorphic vector bundles over a disk, which for non-zero values of the parameter are isomorphic to E, but for the parameter 0 are isomorphic to this thing. So really, subbundles are appearing because they correspond to these kind of degenerations. Or a much more elementary example would be just to consider a complex vector space, V, and our objects just to be endomorphisms of this vector space, linear alpha from V to V. And our preferred, well, our metrical structures are going to be metrics on V, but the condition we want to consider, corresponding to having a flat unitary connection, is that we want alpha to be normal with respect to this metric. So we want H, a metric on V, such that, as to say, alpha commutes with the adjoint we form using H. So now the condition for existence you easily see from what you know about, if you know if a matrix commutes with its adjoint, then it's diagonalizable. And conversely, if it's diagonalizable, you can always choose a metric to arrange that property. So existence is equivalent to saying alpha is diagonalizable, which is equivalent to saying, in a sense, there are no non-trivial degenerations. Because if we take a matrix with a non-trivial Jordan form, like say this one, the simplest example, all of these lie in the same conjugacy class. So we can think of these as a family of endomorphisms, all of which are equivalent for non-zero t, but when t goes to the limit, we get something different. So these degenerate to the zero matrix, and that's how this fits into our general picture. So another thing to say is that part of this story is that we can always obtain these preferred objects by minimizing a certain function. So the preferred objects, so these are characterized by minimizing a function. So in our elementary example here, this would just be the norm of, if we have any h, we can take the norm of our fixed alpha with respect to h, and then take the logarithm of that. And to make the sense of this, we should fix the determinant of h. So if you look at all the metrics with fixed determinant, you minimize this functional, finding a minimum is precisely the same as solving this equation. Easy to check. So this could be known as the Kempfness of the names associated with that statement. So it's been understood for quite a few years now that these questions about the existence of Kaehler Einstein and constant scalar curvature metrics can be fitted at least in a formal sense, into this general pattern, this general scheme. So this is a pattern, a scheme which in fine dimensions produces sort of pretty general, straightforward results. In infinite dimensional examples, such as these gauge theory ones, it's more of a guide to what should be true rather than something that produces theorems automatically because of. So what we want to put together our first section. In the second section, we want to say that these Kähler problems, there are questions in Kähler geometry, can fit into such a scheme, into such a formalism. So these ideas are developed over, say, quite a few years, and we don't have time to discuss systematically how that has gone. Certainly they go back, in the case of Kaehler Einstein metrics, to conjectures of Yau from the 1980s, many years ago, conjecturing that the existence of a Kaehler Einstein metric should be equivalent to some notion of stability. But let's just say what is the notion which one is led to, if one thinks in that direction. Well, what is the precise, initially conjectural criterion one gets for this existence problem? Lost my notes. Well, before doing that, let's make a remark that the relevant geometry involves an infinite-dimensional group G, the group of symplectomorphisms of X. So we take our. So we can think of Kähler geometry. We can think of the intersection of complex geometry, Riemannian geometry, but also symplectic geometry. And it's the symplectic point of view which appears as sort of the key thing in thinking about the underlying structure. But let's not say more about that now. Perhaps we'll come back to say something later. Let me just write down more precisely what this notion of degenerations becomes in this situation. So this involves what's called a test configuration for a pair of a polarized manifold, a compact manifold X, and an ample line bundle L. So this consists of a family, X, as a C. So we have a space with a flat map down to C, a line bundle over the whole space. And this should be C star equivariant. We have an action of C star on C. This is usually my multiplication. And we want to lift that action to this family, to this line bundle. So in the usual way we can think of this, we think of the fibers of this over a point T, as we have a pair xt and lt. And the basic point is that for non-zero t, these should be isomorphic to original pair we started with. Or actually, we need to introduce one more parameter. We take some power m of our line bundle n. So for t not 0. And this line bundle should be, let me just say, relatively ample. It should be sort of ample on the fibers. So it can be used to give an embedding of the whole family into some projective space. So this is our notion of what we mean by the degeneration of a complex manifold in this situation. We're fitting into our general pattern. Then the crucial thing that we want is a numerical invariant of this degeneration, which is going to be analogous to the condition on the first germ class in the case of bundles over curves. Now this numerical invariant is called the Futaki invariant. So that's the Futaki invariant. This is going to be a numerical invariant of these degenerations, but in fact it's going to just depend upon the central fiber, what we get when putting t equals 0, together with the induced C star action on that. We have this C star action on everything, but the C star fixes 0 in C, so it fixes the fiber over, the data over 0. So over 0, we've got a polarized manifold with a C star action on it. So we give two definitions. So one is a differential geometric definition. This only applies only immediate applies in the case when this central fiber is smooth. But we should emphasize that we definitely don't want in general to assume that. Here we're allowing this, so all the fibers away from 0 are going to be smooth manifold that we started with, but in principle this central fiber could be something terribly singular. But at least if we imagine, in fact, we restrict momentarily to the case of a smooth central fiber, then we can define this invariant in a simple way through differential geometrically. That's to say, we consider the circle in C star and a S1 invariant metric on this central fiber. Then this, if we think about this in terms of symplectic geometry, we'll have a symplectic form preserved by this circle action. That action will be generated by a Hamiltonian. And the formula is that the Futaki invariant then is given by taking the integral over x naught of the Hamiltonian times the scalar curvature of this metric minus the average value of the scalar curvature. This means that subtracting off this average value means it doesn't matter if we change the Hamiltonian by adding a constant, which of course we know we could always do. So this is the right normalization. So this is something we can write down, and it's not hard to verify. This is independent of the choice of the S1 invariant metric that we choose. And we can also see that more generally by interpreting this formula as a formula in equivariant cohomology in a certain sense. But let's just note one thing here, which we want to refer to later. If x naught has a constant scalar curvature metric, then the Futaki invariant is equal to 0. That's clearly, because if its constant scalar curvature is equal to its average value, whatever Hamiltonian we have, this integral will be 0. So this is a very obviously trivial statement from the formula, but this is points to the root of this connection between this criteria and our existence problem. You see the scalar curvature appearing here.
Simon, is constant scalar curvature automatically invariant?
I'm sorry?
You need an S1 invariant metric, right?
That's true. That would be true, yes. I agree, yeah. In fact, you could do it, there are setups, yeah, that's true. Yeah. S1 invariant, I agree. Yeah, in fact, we know that by various uniqueness theorems, we know that it will be automatically invariant, essentially. That's a good point. So secondly, let's give the algebrogeometric definition, which has the advantage that it works for any kind of bizarre scheme or something that's the central fiber. So here what we do is we take our line bundle L, restrict to this, so L naught to the K, over, so we consider the sections of the powers of our line bundle over the central fiber when K is sufficiently large and positive. So these will be, these are fine-dimensional vector spaces, and clearly we get an induced action of C star. So we can extract two sequences of numbers from these vector spaces. One is the dimension, the dk, the dimension. And the other is the total weight. The sum of the weights of the one-dimensional subspaces, or just the weight of the action on the highest exterior power. The general theory says that the dk is given by a Hilbert polynomial for large k, and of degree k of degree n, where n is the dimension, and the wk, by slight variant of that theory, is given similarly by a polynomial of degree n plus 1. So if we can take the ratio of wk over k times dk, this is the ratio of two polynomials of degree k plus 1. And so this will be we'll have some expansion for large k as follows. And the Futaki invariant is just this term in the expansion. So that's an algebrogeometric recipe, and using various forms of Riemann-Roch theorem, one can show that in the overlapping case, when you have a smooth central fiber, these formulae agree. So we've almost got there. So do I finish at 10 past? Is that right? 5 more minutes. Yeah. Okay, that's fine. So what we say that a test configuration X is, we say X is destabilizing if this Futaki invariant is negative, 0 or negative. But provided it's not, of course, if you took a trivial degeneration, then that would just take the product, that would be 0. But if you have a non-trivial degeneration with negative Futaki invariant, which simply calls destabilizing. So X is destabilizing if non-trivial, without precisely saying what I mean by that, and the Futaki invariant of X is less than equal to 0. Right, so this is so now we say that X is that XL is K stable if it has no destabilizing degenerations or test configurations. So with a certain sort of goodwill and point of view, you can see this as the criterion that will come from this general picture that we outlined, applied to this, everyone attempts to apply it to this infinite-dimensional situation of involving Kähler geometry. And so to reach a good endpoint, then, the conjecture in the field over the last, more precise conjecture over the last 10 or 15 years or so, is that this K stability should be the criteria for the existence of a Kaehler Einstein metric. So I should say that the version of this definition in this differential geometric point of view was given by Chan in 97, I think, 96, 97. In any case, the main results and development that I want to telling you about today is the fact that this is in fact true. The theorem is that a Fano manifold indeed has a Kaehler Einstein metric if and only if it is K stable. So this condition involving these degenerations is the algebraic criterion or condition for the existence of a Kaehler Einstein metric. See, whatever it is certainly something phrased purely in algebraic terms. It's not, the definition doesn't mention metrics or anything like that. So the theorem is that if X Fano, then X admits a Kaehler Einstein metric if and only if it is K stable. So perhaps now is a good time to stop. As I explained at the beginning of the second half, there are now 4 proofs of this. And so my purpose in the second talk will be to give some rather superficial, say something rather superficial about these 4 different proofs and approaches, and then talk about some applications to specific examples where one can study particular manifolds. But this seems a good place to stop just here.